I honestly am still in awe of Google Maps.
Keep track of my calendar.
I like it when my phone reminds me that people have birthdays that they know I interact with a lot on Facebook, because otherwise I would forget.
My homework.
My smartphone doesn't have the thing where, like, if you have an appointment, it'll add in travel time and kind of pop up with your directions and tell you that you need to leave. So I kind of want that.
Our smartphones and other smart technologies are not really smart. They are powerful and perform incredible feats of computation in fractions of a second, but these actions only take place after a user has initiated that action. Cognitive computing has the potential to make our devices actually smart, learning our tendencies and preferences and taking autonomous actions. We had the privilege of interviewing Dr. Maximilian Reisenhuber, Georgetown University's specialist on cognitive computation. He was able to give us a brief but in-depth view of this burgeoning field.
Yeah, so cognitive computing is the idea that let's look at the brain for how it does complex tasks, right? The tasks that computers currently aren't as good as people, like recognizing objects. So for instance, right, it's a very basic one, recognizing speech, recognizing visual objects. And problems AI has been working on for decades, but the solutions they've produced are still not as good as things we can do, even little kids can do, right, very easily. And so the question is, well, can we figure out how the brain does it and then leverage that to have computers do the task in the same way the brain does? So it's a very different way of thinking about how to do computing. The traditional von Neumann architecture in your iPhone and whatnot, right, it's the idea you have a few processors that are very, very fast, and then they have some memory and they can ship things back and forth, but that's not how your brain works, right? Your brain has 100 billion neurons, hopefully, right, so on the order of, and each one has connections with about 10,000 other neurons, right? So you have this big network of processing units that each one of them is very, very slow, like only 1 million times as fast as current processor, but the power really comes from a lot of these simple units all working together and breaking down the problem, and then this way being able to, in a very different way, do these tasks that we're interested in AI, for instance, right now, and understanding how the brain does. Yeah, I once was riding in a cab, and so the cab driver asked me, so what are you working on? I said, well, I work on vision and how to recognize objects. And he said, oh, vision is easy, right? And the reason it is easy is because 1/3 of your brain is doing just that, right? And so right now, your auditory system is trying to understand my words, right? Same thing. So, but the computation is very hard. What people realize in AI, right, when they try to have computers see the way people do, and the challenge is that you can have the same object look very different on your retina, right? So you now see my face, but if I change the lighting a bit, right, if I move around, right, come closer, on your retina, the pattern changes completely, right? It's different photoreceptors being active, right, to different degrees, and your brain, through several stages, then manages to generalize over all these transformations and focus on, okay, well, what's the identity? What's the object I'm going to recognize, and not get confused by these transformations? And that's what makes it so hard. And a connected challenge is, well, how can you learn then from examples, right? So we humans are very good at learning from some examples. I can show you a few pictures, like of even with kids, right? A few examples of dogs, and you can generalize to other dogs, right? But that's again a challenge if you have to train a computer, and it turns out that computers are much worse at generalizing than humans are. So now the challenge is, if you have all these neurons, right? So you have 100 million neurons, how are you going to wire them up, right? So all the learning happens in how you connect these neurons. And so now the question is, how do you set these connections? And so if you think about the brain and vision in particular, from your eyes to where decisions are made here in frontal cortex, it's about 10 different stages. And so now you have, think about it as like a tree with 10 different levels. And so each one of them has a connection. And so now the challenge is, and that's the kind of deep learning, because you have a deep hierarchy, you have lots of different levels. And so now the question is, well, how do I adjust these weights, right? So, and in particular in recognition, the idea is that I look at an object and I want to have a label. And now if my label, if the program or the network has the correct label, it's all good. But what if it's wrong? We have an error at the top, but now I have connections all the way down 10 levels, right? And so the challenge is, well, how do I know how to adjust this connection down here based on an error that happens up there? And that's the deep learning problem. So recognition is pretty much solved to some extent, right? I mean, so if you can train a network to recognize thousands of different classes, and but now you want to get one level higher. Okay, now you know the meaning. Well, what am I going to do with it? Right? And so there was interesting work, you might have seen a couple of months ago, on training computers to play video games, right? So now you can recognize the objects, and now you want to learn strategies, right? So how can I then optimize rewards in the future, right? And so there's another body of research in AI called reinforcement learning that has dealt with this problem, like in robot navigation, for instance, something that's been used a lot. And so the accomplishment was to combine reinforcement learning and deep learning, and so now you can recognize objects, and you can also then, based on your recognition of these objects, optimize strategies to then make make the robot happy in the future, right? So optimize reward, right? And so that's the first step toward now learning strategies and doing things, right? To sort of autonomously optimize behavior, right? So you have a goal, you know, okay, I'm going to get a reward. And so the computer can now figure out by itself, okay, what's the best strategy of maximizing this reward? And that's a very exciting progress, because now we go to this question of intelligence, right? I mean, how can we have the computer figure out by itself to do certain tasks?